Okay guys, so today we're going to look at what actually is a derivative. So we kind of talked about it a little bit yesterday, but we're going to get just a little bit farther into it today. So we talked about how this tangent line would help us find the instantaneous rate of change. Well, the derivative is going to be the slope of that line. What we're going to start off with is just a picture that looks really similar to what we had yesterday. So we'll have just 2 points and a curve. Let me just redo that. Okay, and if I have my first as x, the corresponding y value would be f of x. And just like that second picture we looked at yesterday, instead of just giving a random name to the second point, what I'm going to tell you guys is the distance between those 2 points, we're going to call that distance h. Okay, so since that distance is going to be called h, then that means that my second x value is actually going to be x plus h, which means the corresponding y value is f of x plus h. So what this means for my graph, let's say I have a certain point on that graph and I want to find the rate of change or the velocity at a specific point. Like let's take just a point right there. If I want to find the instantaneous rate of change, I would need to draw a line that's tangent to the curve at that point and find the slope of that line. Okay, so what we've done so far is we found the secant, which is the average, which I could still do. I could draw that secant line and find that slope. But what I'm going to do instead is find the slope of the tangent line. Now, one way we could do that is if I start with that secant line, as that secant line keeps getting closer and closer and closer and closer, and that distance between the end point of the secant gets closer and closer to that actual point, I can find what that derivative is. Okay, so what's happening there, as something gets closer and closer and closer, we're finding a limit. And what we're doing is we're finding the limit as that distance gets smaller, and that distance was h. So we're looking for the limit as the distance gets smaller until it's non-existent, so as h approaches 0. And it's the slope of the secant line, which we already did. It's the change in y over the change in x, which is f of x plus h minus f of x, so those are my 2 y values, divided by the change in x. And if I want to simplify the bottom, those x's will cancel out, so all I'll have at the bottom is h. So what that is right there is actually going to be very important. That is the definition of a derivative. Okay, so that is the formula we can use to actually evaluate what a derivative is of a function or even at a certain point. Okay, so that's going to be very important for us. Now, to find a derivative, the notation, it could say a couple different things. It could say this, which is f prime of x. So that's one way you could say to find a derivative. It could say dy dx, or it could say d over dx. All of those are just different notations for find the derivative. Okay, so to help you guys make a little bit more sense out of this, we're going to look at some stuff on a graph. So the first one we're going to look at is at a certain point, which is kind of what we just did. Okay, so if you guys look on this graph here, I have my tangent line is the dotted line. Okay, so I'm trying to find the derivative at that point C. So at this point, I'm trying to find my derivative. That dotted line, that's the tangent line. So we're trying to find the slope of that line at that point, and that'll be my derivative, the instantaneous rate of change. So in order to find that, I take that secant line, which is the green one, and as that secant line gets closer, it's becoming similar to the slope of that tangent line. And if you look, that's happening as that h distance is decreasing smaller and smaller and smaller until eventually that h distance is 0, and it's the same slope. Okay, so that's where that limit definition comes from. It's that slope of that secant line as that difference, the h, comes to 0. Alright, so we don't always find the derivative at a certain point. Sometimes we find the derivative for an entire graph. So we're going to look at an example here. Now before I trace it, we're going to try and figure out what this graph's going to look like. So first of all, remember, this is going to be a plot of all of the different horizontal tangent lines. So for example, let's say I draw a tangent line at that point right there. Well, the tangent line of that point would have to be a horizontal line at the top of that curve. Same thing at the bottom of the curve. In order to draw a tangent line, it's got to be a horizontal line. So all the tops and bottoms of curves have horizontal tangent lines. And you guys learned back in Algebra 1, the slope of a horizontal tangent line is 0. So that when I draw the derivative graph here at all of those x values, where the tops and bottoms of those curves are, my graph is going to cross 0. Okay, so then we're also going to look at a couple other points in this graph. If I were to draw the tangent line anywhere in this section, that tangent line is going to be a vertical line. It'll be a different slope each time depending on what point specifically I'm looking at, but any x values in those regions would be positive numbers. And then the same idea, any x values on this side, any point on there, if I were to draw that tangent line, it would be a negative value. So what we're going to do is we're going to watch as this actually graphs my derivative. And you guys are going to see, so the blue line that's on there actually is the tangent line, and it tells you the slope. So there's my slope. It's when it's 0, it's actually at a y value at that x value, the y is 0. Then it's a positive number, so I'm graphing positive y values, and then I'm at 0. Then I have negative slopes, so I'm graphing negative y values, and again I'm at 0, and it keeps going and plots those points. Now if you look, the original graph was the sine graph. Now my new graph is the cosine graph. Okay, so the derivative of sine actually is cosine, but we're going to talk more about that later. Alright, so let's look at another picture. So again, try to think about what this derivative is going to look like before I graph it. Try and think about where this graph is going to cross 0 and when this graph is going to be positive and negative. Alright, so now we're actually going to graph it. So as we watch this blue line, the blue line is the slope. So it tells you the slope there is 9, and then that slope is still positive, but it's becoming a smaller number. And then that slope is 0, I'm crossing 0. Then my slope is negative, so it's a small negative number, then a bigger negative, then a smaller negative, and then my slope is 0. Then my slope is positive, and then my slope is 0, and then my slope is negative. So that blue line is the tangent line. Alright, let's look at a couple more. I want to look at this one. Okay, so if you think about the slope of the tangent line anywhere on this point, if I were to draw a tangent line anywhere on here, whether it's this point, or this point, or that point, it doesn't matter where, that tangent line is going to be the same slope. So all I need to do here, it's going to be the same slope everywhere. So if you watch, whatever that slope is, the slope it says it's approximately 0.2. The blue line's my tangent, it doesn't change, which is why my derivative is that constant number. Alright, and the last one I want to look at is this absolute value here. So if you think about the left part of this graph, okay, those are all negative slopes. So I'm going to have negative points being graphed there, and it's constant. So I'm going to have a constant negative number. The problem though is when I get to that sharp point there at the end. If I try and draw a horizontal tangent on a sharp point, I'm going to run into trouble. Because if I have a point like that, so there's my sharp point, and if I try and draw, I can't really draw a tangent line anywhere on there. It's too hard to see where it's going to be. So, at that point, what happens is we say at that sharp point, my graph is not differentiable. Okay, so it is not differentiable. So what's going to happen here is it's not actually going to plot a point at 0. What's going to happen is it's just going to jump up to that positive number. Okay, so at a sharp point, you cannot find a derivative. Alright, the last thing we're going to do is find these derivatives algebraically using that definition that we just looked at. Okay, so I want to find the derivative of the function 5x squared, and I'm going to find two separate things. The first thing I want to find is f prime of x, which is just the derivative of the whole function. Okay, so kind of what we were graphing there at the end. Then the last thing I want to find is the derivative at a specific point, when x is equal to 3. So in order to do this first is I need to find the derivative of 5x squared, and I'm going to use that limit definition from the very beginning. So it's the limit as h approaches 0 of f of x plus h minus f of x, and that is all divided by x plus, or just divided by h. So the first thing you need to find is f of x plus h, which means everywhere there's an x, I plug in x plus h. So f of x plus h is going to be 5 times x plus h squared. And that is my f of x plus h. Then the rest of that equation stays the same. I have minus f of x, which we know is 5x squared. It's all divided by h, and I'm doing the limit as h approaches 0. So it's really the exact same thing we've been doing. I'm adding that extra step of it's the limit as h approaches 0. So now I'm going to do that math here. So I've got 5 times x squared plus 2xh plus h squared minus 5x squared, all divided by h. So I get 5x squared plus 10xh plus 5h squared minus 5x squared. Again, all divided by h. And I can start canceling some things out. Again, remember, I'm doing the limit. Keep forgetting to write this. The limit as h approaches 0. Now my 5x squared will cancel out with a minus 5x squared. And both those remaining terms have an h in them, so I can divide an h out of each term. So what I'm left with now is the limit as h approaches 0 of 10x plus 5h. And now at this point, if I plug in 0, I'm not going to get 0 over 0. I can just plug in 0 for h, so I get 10x plus 0, which means my derivative is 10x. Now I can use that. That's the derivative of the entire function. I can use that derivative now to find the slope of the tangent line at any single point in this graph I want to. So for example, if I want to find f prime of 3, all I need to do is plug in 3 to my derivative. 10 times 3 is 30. So when x is equal to 3, the slope of my tangent line is 30. The instantaneous rate of change at that point is 30. And I can use that for anything I want to. I can do f prime of negative 2, and I can get the slope of the tangent line at that point too.